Hi everyone, I'm Hung-Ming from National Tsing-Hua University in Taiwan. And my advisor, Professor Jenq-Kuen is also here with us today. And our talk today is aggregation optimization for SIMD everywhere from RNeon to RISC-V Vector and crypto extensions. So first, I will cover how to use the open source project SIMD everywhere to convert RNeon Intrinsics to RISC-V Vector and crypto extensions. And we will introduce how we implemented this using the RISC-V Vector Extension and also the crypto extensions. And then I will introduce our aggregation optimization method, which can further improve the performance of the resulting RISC-V Vector programs. Okay, so this is the motivation behind this work. So if you want to move from RNeon program to RISC-V platform, there will be a lot of porting work need to do because many libraries have optimized using SIMD Intrinsics like the RNeon Intrinsics. And if you want to manually rewriting all those intrinsics into like RISC-V Vector Intrinsics, it will cost you many time and you may introduce lots of bugs during the process. So there's an open source project called SIMD Everywhere that's trying to solve this problem. And SIMD Everywhere is an open source header-only library which provides the portable implementation of this SIMD intrinsics. So it already supports different popular SIMD intrinsics like the x86, AVX intrinsics, and also the RNeon intrinsics. And we further enhance this to convert the Neon intrinsics into RISC-V SIMD intrinsics, including the vector extensions and also the vector crypto extension. And for future, probably the RISC-V P extensions. So here is how the SIMD Everywhere work really works. So on the left-hand side is how to use the SIMD Everywhere libraries. If you have a C program with Neon intrinsic inside, you can just include the SIMD Everywhere header and directly compile it using the RISC-V toolchain and compiler. And it will produce the RISC-V vector code. So how this SIMD Everywhere really works under the hood is that inside the SIMD Everywhere header, it will define a macro that will substitute the RNeon intrinsics into the SIMD Everywhere internal intrinsic functions. And then there will be you need to implement that functions either using the RVV intrinsics to directly implement it or use the general portable scalar loop and then rely on the auto-vectorizations to generate the RISC-V vectors instructions. And we have already enhanced and contributed our RVV implementations upstream to the SIMD Everywhere repository. And if you are interested in, you can go to try it and probably improve it with like better performance. And besides the vector extensions, we have further moved on to the crypto extensions. So why this crypto extension is important? Because on the thread of the quantum computing, there will be a potential threat of breaking the traditional encryption algorithms. So NIST have approved several algorithms which need this kind of crypto extensions to compute them efficiently. And when we implemented this kind of Neon intrinsic, crypto-related intrinsic using pure RISC-V vector extension, we find that it is hard to implement it directly because they are not mapped like directly. So with the help of RISC-V crypto extensions, we can more easily to implement this kind of Neon intrinsics, for example, the polynomial type arithmetic or the AES encryptions. Here's the one example of this intrinsic. So this is a polynomial type vector multiplications. And on the left-hand side is that if we use the pure RISC-V vector extension, we need like this whole bitwise operations to complete these operations. But with the vectors crypto extension, we can utilize the careless multiplications to compile these polynomial type multiplications. And here's another example, which is the bit reverse order intrinsics in Neon. So on the left-hand side is if we use RVV to implement it, it also requires a lot of bitwise operation to complete it. But with the crypto extension, we can use the VB-RVV intrinsics to map it more suitably. And during the implementation process of this kind of intrinsic, we have encountered some issues. The first one is that if the Neon intrinsic does not have the direct match to RISC-V vector, we will need lots of instructions to complete it, and will gain a lot of overhead. And the other one is that the AES encryption round trip, the Neon side and the RISC-V side had separate them differently. So if we convert it in intrinsic level, it will have a lot of overhead. And one of our co-authors, Wang, have published this optimization, which can solve this problem in the ICP-PEMS. So if you're interested in it, you can refer to this. Then now we move on to the vector aggregation optimizations. So our SIMD error conversion will limit the potential performance because the Neon intrinsics have a maximum vector length of 128 bits. So if we convert it from Neon intrinsic to RISC-V vector extension, we can only use the fixed length RISC-V vector extensions and not utilizing the potential like longer VLAN or even using the LMO feature. So we propose a LLVM optimization path we called it DLSP to solve this issue by aggregating the short vector intrinsic together and to try to form a longer vector, just like the vector version of auto-vectorizations. So here's a quick view of how we can achieve better performance by applying these optimizations. So on the left-hand side is an XNNPACK operators, the square difference, and you can see that they are implemented in unroll way, and you only use the 432-bit elements to complete it. And the left-hand side result is that it's compiled using our RVV-enhanced SIMDe everywhere. So if we just tweak the program by hand manually, we use the L mode equal to and set the vector elements to 8 elements. We can get the 1.8 times speed up in terms of dynamic instruction count. So here's our DLSP overview. Our DLSP will collect the short intrinsics together and form a longer, wider vectors. And we utilize 3 main compiler optimization techniques. First one is the loop unrolling. We want to unroll the loop to expose more aggregation candidate. We can get more short vectors to aggregate to form a long vectors. And the second one is superword level parallelism, which is a kind of vectorization technique for the scalar program. And we use this concept to find a potentially isomorphic instruction, which is the instruction that we can group together to form the wider vectors. And the third one is the interesting part is that we utilize a technique called data access functions, which we can track the index access pattern of a vector type. Because unlike scalar, the vector program, we won't have the same data type vector length throughout the program. We will have mixed lengths, and it will need to have the more fine-grained information to perform and generate correct code. So here's a quick view of what is this SLP look like. So SLP is the vectorization technique, and unlike loop vectorization, it did not rely on the loop structures. So it will first try to build dependency trees and combining those trees by finding the isomorphic instructions together. And they will produce vector program from the scalar program. So how do we apply this concept or process into vector programs in our problem? So actually, there's some challenge when we applying that to vector program. It's because unlike the scalar program, we may have mixed vector length computations. For example, in this example, we will have 4 times I32 bit type and also have 2 times I32 vectors. And the right-hand side is the unroll and the tree loop of this computation. And we can see that it results in a strided access pattern, which is not contiguous 0, 1, 2, 3, it is 0, 1, 4, 5. So here's the wrong way of aggregating it. If we naively doubling the vector length of each instructions, we will get the wrong result because it is a strided pattern, and if we just widen the extract instruction, we will get the wrong shuffle. So to get the correct answer, we need to insert the correct shuffle. And the shuffle vector is the kind of rearrangement of the vector. And so now we need to have the 0, 1, 4, 5, and insert it to replace the extract instructions to actually get the correct wider vector. And how we achieve this? We achieve this by utilizing this data access function technique. And data access function is basically using a mathematical function to represent the operations. So it can help to trace more fine-grained index access instead of treating a vector variable as a whole entities, and can help you to perform data analysis and also operation synthesis. And it has been used in like other array programs like the Fortran 90 and also OpenCL. So here is how we exactly use the data access function in our DLSP. So on bottom, we can see the on the left side of the arrow is we naively construct the data access function of each vector value from the SSA vector. We can only get trivial information. But after the data flow analysis, for the %1 vector, we can now know that it's actually a base vector A just with some different arrangement of the index function. So with this information, we can perform more data flow-based optimizations, like the previous mentioned insert vector shuffle. We can first analyze the bundle tree and then use the index function to detect every mismatch between vectors and insert the correct vector shuffle accordingly. So for example, if you use a vector and its shuffle is not correctly in there, the reaching definition did not have those vectors, we need to insert a shuffle. And the other optimization is the dead element eliminations. Just like the decal elimination, we can track the live elements and then eliminate the computation that is dead and to eliminate the overhead. So here's our experience setup. We implement our path on the CLAN version 17.0.1, and we set the vector bits of RVV to 256 bits. And we evaluate our work on Spike using the dynamic instruction count. And our benchmark is using the XNNPACK, which is the neural network operator libraries that is implemented using RISC-V Intrinsics. So the first experiment is we compare the original SIMD everywhere conversion with our RVV-enhanced SIMD everywhere. So we can see a 1.07 speed up to 5.07 speed up in terms of dynamic instruction counts. And the original SIMD everywhere flow isn't just convert to the scalar program. It also have utilized the auto-vectorization and also the vector building functions to produce the RVV program. But we can still outperform it because we directly use the RVV intrinsic to implement them. And the other one is that we further apply our aggregation on the RVV-enhanced SIMD everywhere flow result. And we can further gain more performance from 4 times to 11 times. And we perform this experiment on different Elmo settings because our algorithm will test the maximum vector length available. So in this plot, something interesting is that Elmo 8 is not always outperformed than Elmo 4 in terms of dynamic instruction count. It may be because of the register pressure or other factors. And so in summary, we have enhanced the SIMD library for intrinsic migrations from the Omnium to RISC-V Vector Extension, and we have contributed them upstream. And we also improved the SIMD library performance using the RISC-V Cryptography Extension. And we have proposed the vector aggregation optimization, DLSP, which can further boost its performance. And our ongoing work is that we need to come up with better heuristic for like most and the unrow factor selections. And thank you all for your attention. Yes, thank you.
Thank you. Thanks, very interesting talk. I just want to point out it's not fair to use dynamic instruction count to measure speed up, because most of the program you're running, it's not going to stress the front end a lot. And when you crank up the Elmo, your machine is probably spending more time, executing those instructions. So you're not going to get like 11x speed up. Have you considered to run this on some of the open source projects? Like Jerry just released the vector extension to the Rocket, and I heard there's some other open source project that has the crypto extension supported.
Yeah, it's definitely better to get real statistics from real hardware or like have a simulator with memory model. But since we mainly want to eliminate different microarchitecture effects, so we still think that dynamic instruction count is a fair metric for reference, but it is definitely better if we have other statistics reported. So we will try to conduct experiment on the simulator with memory model or real hardware, yes.
Thanks. One follow-up question. How did you implement a shuffle? I don't think there is a shuffle instruction in the extension.
Shuffle, so this path is using the LLVM to implement. Okay. So we transform the RVV intrinsics in LLVM IR. So the input-output is all LLVM IR. So the shuffle vector is LLVM IR instructions.
Oh, so it's not mapped to a particular vector instruction? So this is a...
Yeah, our optimization path is implemented in LLVM. So it's okay. A LLVM optimization path. Yeah, and the input program is we compile the C program with RNA intrinsics and include the SIMD library header. So inside the LLVM IR, it will be RVV intrinsics in LLVM IR form. So it's IR in IR.
I was curious how this is implemented, because one way you can do shuffle is you can use a VR gather, which is a very expensive instruction. So if you just count this as a one instruction, it will be not fair, because this one will spend...
but the shuffle instruction will count the actual RISC-V instruction, not the LLVM IR instruction.
Oh,
because,
even on the RISC-V side, it's one instruction called VR gather, and I can imagine a lot of implementation
in hardware. I got it.
It will spend hundreds of cycles processing this. Okay, thank you.
Thank you.
Share contact info. Okay, I think that's all the time we have for questions, unless there's a really burning one that we need to do. Okay, thank you very much again.